All right, guys, so this in this video, in this segment, I want to talk about a specific special case of accelerated motion, and that's free fall. So free fall, this is a case where an object is falling, so it's moving through space, and it's acted upon only by gravity. So gravity is the only force that's influencing this thing. So we're ignoring air effects such as air resistance. So we can think of this is falling in the absence of air, which means you're not going to get any sort of retarding force from air. You're also not going to get any of these other air effects like curvature, or change in trajectory due to air pressure differences, for instance. So this is the special case of free fall. And in the case of free fall, if there's no air resistance, if the only thing acting is gravity, it turns out that we can treat gravity as an approximately constant force, and therefore the acceleration is constant. So this is a special case of uniform acceleration. So the acceleration value is equal to what we call g, the acceleration due to gravity, which has a value on Earth of about negative 9.8 meters per second squared. So this little g is used to represent the acceleration due to gravity. Acceleration due to the force of gravity. And the negative sign here is I throw that in there because typically we think of down, we define down as the negative direction. So down is defined as the negative direction. So that's the reason we throw in that negative. And so you'll see frequently in equations that free fall equations that we'll use g rather than a. We'll throw this letter g in place of a to indicate that it's the acceleration is this special value of 9.8, negative 9.8. So this is a uniform acceleration. As I said, we're treating it as constant, which near the surface of the Earth is a fair assumption to make. I want to point out this is a pretty significant acceleration value. What this means is that every second the object falls in free fall, its speed increases by a value of almost 10 meters per second, right? So that's pretty significant. To put it into context, at this rate of acceleration, an object will reach 60 miles an hour in just over 3 seconds. Some of you, if you know anything about cars, for instance, there are very few cars that can go from 0 to 60 miles an hour in under 4 seconds, and we're talking about just over 3 seconds here. So this is pretty significant. So what I'd like to do, we've talked a little bit about acceleration, but the way I'd like to actually think about this is by taking a look at some graphs. So let's imagine a case where I'm on the ground. Here's the ground, and here I am. That's me, and I'm throwing a ball up into the air. So here's this ball, and I'm going to throw it up into the air. So it's leaving my hand with a certain velocity, v naught. And it's starting at a certain position. This position right here is x naught. So it's the starting position, and it's thrown upward with an initial velocity. So we're going to call this initial velocity, right, that's positive. And I'm going to call x naught. Let's just think of that as the 0 position. And this, what's going to happen? Well, this ball is going to go up, 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 up. And what happens to its velocity as it goes up? Well, the velocity, what's going to happen to it? It's going to decrease. It's going to decrease until it gets to the very, very top. And at the top here, this velocity at the very, very top is 0. And we can think about this. This is a certain position x, but it's gone up. And it's gone from some positive velocity to 0. The velocity has decreased. And that makes sense because we're calling this negative. So this implies that the velocity is always decreasing. So it goes from some positive value to 0, and then it falls back down. So then it starts to come back down now, right? It's going to start to come back down. And what happens as it comes back down? Well, the velocity is going to continue to decrease, right? Now, that might be a little strange because we know, of course, the speed is increasing, but the velocity is decreasing in the sense of becoming smaller than 0. The velocity is now downward. It's now negative, less than 0. So the velocity is decreasing over the entire interval. So here's the path up to the top. It stops for an instant, and then it starts to come back down. And then I want to imagine that I catch the ball again at the original height that it was thrown. In other words, we're going to imagine that our delta x is 0. And that's important. Delta x is 0. I catch it at the same height that it is thrown. And now what I'd like to do is to make some graphs of this trip. So we could start off, this is not maybe the most exciting graph, but we could go ahead and plot the acceleration against time. So here's acceleration on the y-axis and time on the x-axis. And we know, of course, what's this going to look like? Well, the acceleration is a constant negative 9.8, so just a horizontal line, negative 9.8. Uniform acceleration. The entire time, the acceleration is negative 9.8. Here's the time when I throw the ball, and here's the time when I catch the ball. So for the entire time, the acceleration is negative 9.8. Notice that I haven't thought at all about, to be really careful, t equals 0 is the moment the ball leaves my hand, right? And the end of our little interval here is the moment the ball hits my hand. So I haven't considered the acceleration of when I'm throwing the ball, when I'm accelerating the ball up, or the deceleration when I catch the ball to stop it. Well, let's think about what this would look like. What would this graph look like on a velocity time graph? So this is now a velocity time graph. Okay. Well, what's the relationship between these graphs? Well, I know that the value of acceleration here is going to give me the slope of the line here, because I know that acceleration is the derivative of velocity, and therefore this value, the acceleration value, gives me the slope of the line. So I know I'm going to have a negative slope, but where do I begin? Well, we said that the initial velocity, v naught, is positive, so I'm going to start here. This is v naught, some positive value. And what happens? Well, I need a negative slope. Okay, so a negative, by the way, a negative constant slope. So I'm going to draw a constant negative slope, something like this. Ooh. Try that again. Something like that, constant negative slope. And what's happening here? Well, the velocity, let's think about this first little interval from here to here. What's happened here? We started with a positive velocity, and then at this point, we're at 0 velocity. So what is this 0 velocity point? Well, that's this, right? That's the top. This is the very top. That's what that is. That's the very top. The top, what we would call the maximum height. So maximum height is this point where the velocity is 0, right? That's a transition point. It's going up. This entire point, right? This entire line segment is the object is going up. Why? Because my velocities are positive. From above the t-axis, I have positive velocity. That implies that the ball is going up. Now, I dip below the t-axis. What does that mean? Well, the meaning of that, of course, is that now the velocity is negative, so the ball is coming down. So this right here is when the ball is going up, and this right here is when the ball is coming down. And we're beyond this point right here, up and then down. Hopefully that makes sense. You know what I want to mention? Let's think about this velocity down here, right? This is the velocity. This is, in some sense, the final velocity, v, at the very, very end. I want to think about what the relationship is between the initial velocity that I threw it with and this velocity, right? This is the velocity that I catch the ball with. Well, let's remember we have an equation that we had a couple of videos ago that said that the velocity squared is equal to the initial velocity squared plus 2 times a times x minus x naught, the displacement, right? That was one of our equations. Now, I should point out, this equation can only be used for uniform acceleration. Well, we have free fall, which is uniform acceleration. And let's take a look at this equation. Well, what do I have here? I have this velocity. I'm interested in what that velocity is. I've got the initial velocity. This is g, negative 9.8. But what's this? What is the delta x? We said that the delta x is 0, right? I throw it here, and I catch it at the same point, which means this entire term vanishes. This whole thing goes away. And what does that mean? Well, that means I have v squared is equal to the initial velocity squared. In other words, positive negative v equals positive negative v naught. Or another way of saying that is the speed, the absolute value of v that I catch it is the same as the speed, absolute value of the velocity that I threw it with. In other words, I throw the ball up at a certain speed. When it comes and returns to my hand, in the absence of air resistance, same speed. The absolute value of this is equal to the absolute value of that. They're opposite in sign, but they have the same value. All right, last graph. It might be interesting to take a look at position as a function of time. So here's t, and here's position x, increasing on the axis here. Well, again, it's similar to the last exercise we went through. The value of the velocity tells me something about the slope of this graph, right? So let's think. Well, I begin with a large positive velocity, so I need to begin with a large positive slope. Well, here's zero velocity, right? That's zero slope, flat line. And this is a large negative velocity, so it's a large negative slope. So I'm going to end up with something like this. Okay, slope begins a large positive value and it diminishes and diminishes and diminishes and goes to zero, and then the slope becomes negative and it becomes increasingly negative until I catch it. So this would be the graph of the position with respect to time. In equation form, we can say here this is the acceleration is just equal to g, negative 9.8. The equation here, what would this look like? Well, we could say that the velocity at any time is equal to the initial velocity minus gt. Notice I put a negative in here, right? The equation that we have is v equals v naught plus at. But I put a minus sign because I know that g is negative. So that this negative comes from the fact that g is always a negative value. And I could say that the position here is equal to the initial position plus v initial times t minus 1/2 gt squared. Okay, so these are old equations, but adapted to our use. So we put in, for acceleration, we've substituted in a g, right here, and right here I've substituted g in for a, and then I've also included some negative signs to indicate that the acceleration value is in fact down. It's accelerating downwards, so that's a negative acceleration. I'm going to leave it there for now. We're going to use free fall a lot. There are a lot of cases where the relevant, in physics, there are a lot of cases where the relevant acceleration is the free fall acceleration. So this is going to be used quite a bit. But I'm going to leave it there for now.